Think math can't predict the future? Well, today we're hacking the illusion of probability.
Let's zoom in. What are the exact odds two people in your math class share a birthday? Feels impossible, right? But mathematically, with just 23 people, it's actually greater than a 50% chance.
It's the ultimate clash. Theoretical probability, what we expect to happen, versus experimental probability, based on actual data.
Say we roll a weighted dice 60 times. The data reveals a heavy bias. Not all numbers are equal. Zooming out, we use relative frequency to predict the next roll, successful outcomes divided by total trials.
Simplify that data to a fraction, multiply by 100 future rolls, and boom, you predict 23s.
We can totally reverse engineer this. If a 2 rolled 38 times, we can actually estimate the total rolls.
This literally applies everywhere, like a bird spotter logging 130 sightings over a 5-hour span. To mathematically predict tomorrow's flock from that data, you've got to assume environmental conditions remain completely constant. Zooming back in, check this 20-day bus commute log. Over half the time, it arrives perfectly on schedule. Here's a classic exam trap. Scale that tiny 20-day sample up to a full year to predict total delays. But remember the golden rule, guys? Small samples lie. For real accuracy, you must drastically increase the trials. Now, witness the probability drop. A single marble falls, randomly bouncing left or right through a totally chaotic maze. In a tiny 2-row system, only 2 routes land a marble dead center. Left-right or right-left. But scale that up to 10 rows, it triggers a massive, mind-bending mathematical explosion of possible routing outcomes. Experimental probability always converges on theoretical truth. So how do those chaotic marbles perfectly recreate Pascal's triangle? Keep calculating.